Hello, my name is Tae-Hoon Moon from Chunghwa University, South Korea, and the title of my presentation today is Projecting Impact of Climate Change and Exploring Policy Measures to Mitigate Climate Change Impact in South Korea. This is a product of co-work with Dr. Yeora Chae from Korea Environment Institute, Dong-Seung Lee, doctoral researcher at Spatial Information Industry Promotion Institute, and Professor Dong-Hwan Kim from Chunghwa University. The purpose of this study is to analyze the impact of climate change on urban-rural economy, society, and biodiversity of South Korea, and explores policy alternatives to mitigate this impact. I'm going to skip review of existing studies to save time and going directly to model. Figure 1 shows a simplified structure of the climate change impact model. In the model, the climate change impact is structured as coming from three sources: sea level rise, extreme climate phenomena, and temperature rise. All or some of these factors affect several selected areas, such as urban and rural areas, population, energy, and water capacity, and biodiversity. The climate change impact on these areas incurs a direct damage cost, restoration cost, and cost for response preparedness. Increasing the total cost negatively affect the national economy and gross domestic product, GDP. This in turn affects the government budget expenditure for climate change response. This climate change impact model can be translated into a causal loop diagram as shown in figure 2. The diagram shows the relationship among the variables and interactive and circular effects of climate change on urban and rural areas, population, water, energy, biodiversity, forest, national economy, GDP, and government budget use, and investment for climate change response. This causal loop diagram was translated into a stock flow diagram for computer simulation. Climate change impact model has four sectors. The first one is this one, urban, energy, industry, and bio and budget sector. The second one is the rural, food, and water sector. The third sector is population, and the last one is social and environmental sector. This slide shows simulation result. A climate change scenario with a representative concentration path, RCP of 8.5 was used for this simulation. Figure 3 shows that the total damage cost induced by climate change is continuously increasing in the simulation period from 2000 to 2050. The health impact damage cost and cost related to the decrease in biodiversity were higher than personal damage due to earlier death, damage to livestock, and forest. This slide shows comparison of urban and rural area damage. Figure 4 shows the damage area due to climate change, and figure 5 shows the damage cost in urban and rural area. The simulation result shows that the blue line one, this one, total damaged rural area is about 7 to 8 times larger than that of urban area, red line 2. Damage cost in the urban area, red line 2 here, is about 5 times higher than that of rural area, blue line 1 here. However, figure 8 shows a comparison of the industrial output damage cost per person between urban and rural areas. We see that cost in the rural area, red line 2 here, is about twice higher than in the urban area, blue line 1 here. This result, taken together with figure 4, that shows a larger submerged rural area, suggests that rural residents' perception of climate change damage could be higher than that of urban residents. This implies that rural residents' perception must be considered when allocating climate change adaptation budget to rural areas. Otherwise, it could trigger a conflict between urban and rural residents regarding fair allocation of budget resources. This slide shows several policy test results. The figure compares climate change damage in several areas with different scenarios, RCP 8.5 and RCP 4.5. Figure 15 and figure 16 shows that social and environmental damage and total damage is bigger than RCP 8.5 scenario than with RCP 4.5 scenario. However, GDP, as shown in figure 17, industrial output decrease in urban and rural areas, figure 18 and figure 19, and industrial output per unit of urban area due to sea level rise is much larger than RCP 4.5 than with RCP 8.5. Thus, we can say that decreased social and environmental damage with 4.5 scenario compensate increased industrial output damage and resulted in decreased total damage and increased GDP. Policy implication might be that the climate change response could be improved by focusing on measures that can maintain industrial output in the short run, as well as policy measures that can reduce social and environmental damage in the long run. Figure 21 explains these points further. I'll skip this slide. This slide shows GDP change with climate budget change. Figure 23 shows that the GDP change when the climate change budget is increased from 3% to 5%. The amount and proportion of GDP increase due to the increase in the climate change budget is much higher than the climate change budget increase. Figure 24 illustrates the increase in the climate change budget when the share increased from 3% to 5%. It is interesting that 2% increase in climate change budget resulted in a much higher increase in the same budget by 2050. This is because increased climate change budget decreased climate change damage and consequently increased GDP. This in turn increased the total amount of the government budget and the climate change budget. This cycle with consecutive results has a virtuous cycle effect, as we noted earlier. Figure 25 shows the change in climate change damage when the climate change budget is increased to 5% with increased budget. With increased budget, the total climate change damage is reduced from about 13 trillion won to 11 trillion won, and the slope of the climate change damage is decreasing, albeit very slowly. This slide shows result of policy test on the impact of heat waves on water and energy demand. Heat wave increase energy cost by at least 3.5 times and decrease GDP by more than 200 billion won. In figure 28, the impact of heat waves on water demand is almost negligible. This is because the decreasing population trend reduced the water demand substantially. Last part is discussion and policy implication. First, most feedback loops in the causal loop diagram are positive feedback loops. When the climate change budget is increased and the climate change damage is reduced, both industrial output and GDP increase. This increased GDP can allow more budget for climate change response, leading to reduced climate change-induced damage, which in turn increases the industrial output, forming a virtuous cycle. Early and large investment is crucial for success of environmental damage reducing policy. Second, regarding the cost of climate change-induced damage, the cost from a loss of biodiversity is estimated to be the highest, followed by that from health impact, food import, livestock damage, industrial output decrease in the urban area, forest damage, and industrial output damage in the rural area. Third, when comparing climate change damage, the total damage is larger in the urban area than rural area. However, the damage per capita and the size of damaged area is higher and larger in rural area. This implies that the psychological damage might be higher in rural residents. So when allocating climate change budget resources, more careful consideration need to be taken in order to prevent conflict between peoples in urban and rural areas. Fourth, industrial output decreased much more under the RCP 4.5 scenario than the RCP 8.5 scenario. This indicates that even if efforts to reduce the impact of climate change to the RCP 4.5 levels are made worldwide, it would be crucial to undertake a policy measure simultaneously to mitigate the decline in industrial output. Lastly, although heat waves affect both energy and water demand, the effect is stronger on energy demand. Therefore, it is necessary to prepare policy measures to improve the energy supply and demand problem. Since an early and large investment to expand energy supply can increase industrial output and form a virtuous circle in the energy sector, it is important to consider this policy direction seriously. Moreover, for this policy to be effective, measures to reduce the energy supply costs are necessary. Otherwise, a vicious circle might be created. This is all for my presentation, and this is a reference. Thank you very much.